Good morning, everybody. Welcome to Cloudy Overcast Tuesday morning at Chem 1211 with your host, me, Dr. White. Now, I just corrected the original announcement for six, quiz six, which will be given on Wednesday. Let's take a look at it on Blackboard. And what I corrected is you'll have until Thursday. I had Wednesday there, bad Dr. White. But anyways, tomorrow, right after class, around 11 a.m., I'll send out the password for quiz 6 PDF file. You'll have until Thursday, 11 a.m. Take quiz, upload it as a single PDF file. Remember, I'll take off points if you don't follow directions or if you're late. And as I said, quiz 6 has 6 pages, 10 problems, and it's worth 55 points. It covers chapter 14, which is Bronsted-Lowry acids, bases, chemical formulas of key acids and bases, conjugate acids, conjugate bases, which I'm going to go over again right after I'm done with this stuff, and water dissociation reaction, the ionization constant of water, Kw, not named after me. Shucks. But anyways, acidic solutions, basic solutions, neutral solutions, pH determination calculations, buffers, and titrations, which I covered yesterday. All right. And let me do this. Go into student view. Go into announcements. No, not announcements, assignments. And you'll see it's now available for your download, quiz 6. Here's the PDF. I had put a periodic table, but I don't think you even need it. And here are the instructions I've been using all semester, plus if you haven't used it, CAM scanner in case you need it. I know a number of your colleagues have used it, and it looks like it's working out well. So once again, don't forget, tomorrow after class, I will send out the password for quiz 6. Now, speaking about the future and what's happening, let me remind you, next week it's on the schedule. You'll have the whole week, and I'll do it from Tuesday through the end of the week, and then the following week to take test 2, which you have to take at the COD testing center. Now, later this week, I guess by tomorrow morning, I better get my act in gear. I'll give the breakdown for test 2. My test 2 is essentially my final, that way I can keep the ACS final very tiny points. But I'm not allowed to technically give it during finals week, so that's why I have this week. But I'll explain that to cut down on my driving. Gas is expensive and I'm lazy. Instead of having to go on Saturday and pick up the test, and then 2 to 3 days later, go back and get the final to grade, I will just go Wednesday morning. So what does that mean? Well, let's look at the internet. All right, you should see a calendar on the screen. Thumbs up, people. Do you see December? Thank you. Now, today's the 29th, and the week of the 5th, starting that Tuesday through Wednesday morning, the 14th, you have to be done by 11 a.m. You'll be able to take test 2 at the testing center. I got to send it to them too. this week. Also, starting on the 12th through the 14th, finishing, you have to be finished because I'll be there at 11 a.m. on Wednesday. You can take the final exam. Now, what I highly recommend is wait until Thursday or Friday or even Monday to take test 2. Now, you can, if you want, take both at the same time. Take test 2, then take the ACS. I'd recommend that order. Or you can do it on separate days. But both have to be finished by the 14th at 11 a.m. because that's when I'm going to be there to pick it up. And if you haven't finished, guess what? You'll get a 0. But that gives you plenty of time. Now, why am I saying, even though you can take it on the 6th or 7th, wait until, I don't know if they're open on Friday, but you can take it on the 8th or the 10th, but whatever their hours. Why wait until later the week? Because Monday, Tuesday, and Wednesday, I'll be spending a total of 6 hours doing a whole semester review of what's important and what you should know. So I'll be putting this out in a memo by Saturday, but I'd highly recommend you wait until after I do the review. Now, if your schedule doesn't permit it, well, that's up to you, but my test 2 will cover the whole semester. I see a question. And the answer is, I believe they are open on Saturday. Let's find out. So much for not finding things easily. Huh. I usually can find it very quickly. Here it is. They have it hidden at the top. Everybody see the PDF on your screen? Let me make sure. Okay. All right. Glen Ellen, they're closed Friday. And now special hours. Now, notice at the bottom, December 9th through 13th. They're open Friday, the 9th, which means you can go there. Normally they're closed. They're open Saturday and Monday and Tuesday. You see their hours. I'll have to email the director. I guess the rest of the week they're the same, but I'll have to check. Maybe you got to get yours done by Tuesday, 7 p.m. Maybe I've got to get there if they're not open on Wednesday. Yeah, well, I'll have to check into this. I'll email the director today or tomorrow. But anyways, here are their hours. If you're looking for it, at the very top, if you put in Google COD testing center hours, take you here and see this little green box, click on it, and that's the PDF I have here, which, you know something, I'm going to download this since I probably will be using it again. All right. And you can only take the test and the final at Glen Ellen, none of the others. Okay. Any other questions about upcoming? Look at my chat. All right. Now, I don't remember if I did this yesterday, so I'm going to go back and do it now. Everybody see 4 points on their screen now? And abbreviate conjugate acid and conjugate base. All right, let's look at the following. I'm going to do this one. Then I'm going to let you have fun too, and I'll do one, let you do one. So the question is 4 points. For the following reaction, label the following as acid-base, conjugate acid, conjugate base. What's a conjugate? It's a molecule that differs by only H plus. So for students, I've found, just think of it as H. So first of all, you have to find the conjugates. And an easy way to do that is, well, if it only differs by H plus, this has a phosphorus, this has a phosphorus, water doesn't. So these have to be conjugates. Next, here I have OH and H2O. Think of just an H, even though it's H plus. So these are conjugates. So now we know the conjugates. Now, by definition, the right side is always the conjugate. So immediately I can write down here, conjugate. Now, when W goes to its conjugate Y, does it lose a proton or gain one? And it goes from 3 to 2, that's a loss. Something that gives up or loses a proton is an acid. Now, if you look at X going to its conjugate Y, it has OH, one hydrogen, and it picks up H plus, or just count the hydrogens, it's easier for you, goes to 2, so did it give up or accept? It accepted. What's something that accepts a proton? A base. Now going the other direction, this way, because we are just going from left to right, now going from right to left. If we look at Y, this is called the phosphate anion. If it goes to W, does it gain or lose a proton? Think of H, goes from 2 to 3, so it's gained. What's something that accepts or gains a proton? And the answer is a base, but since it's on the right side, it's the conjugate base. Now look at water, goes from Z to its conjugate X, and here, does that gain or lose a proton? Count the hydrogens, 2 to 1. It lost the proton. It gave it away. What's something that donates a proton? And that's an acid. And because it's on the right side, it's a conjugate acid. Remember, the right side are always the conjugates. All right, I'm going to let you have one to try on your very own. And I don't rewrite the instructions, but let's see. Nope. And you have to label X, W, X, Y, and Z, acid base, conjugate base, whichever ones they are. Your turn.
Can we label like A, B, C, D or 1, 2, 3, 4?
Well, what you would put in, like I did above here, one of these four letters is acid, one of these four letters is base, one of these four letters you should identify as conjugate acid, and one of these four letters you should identify as conjugate base. Does that help?
Yeah, so it doesn't really matter what letters we're gonna use.
No, doesn't. I could have put down GH, whatever, or I could have used numbers too, 1, 2, 3, and 4.
Okay, so on the test, we're just gonna have question and reaction, right?
Right, here's the
Okay.
reaction right here. And you have to identify W, X, Y, and Z as either acid, base, conjugate base. Again, 1 point for each answer, 4 answers, 4 points. And thank you for your question. All questions are good questions in my class, in my life. Hopefully in yours too. Yeah, like I said, this is something I realized I didn't think I had in the problem set. So I figured I better do 2 today. And I am. This one's a little tricky, I just realized. Because both X, W, and X and Y and Z have nitrogen, but there's another atom that's different. So you can easily find the conjugates. And when you're done, give me a thumbs up, or when you want me to get going, give me a thumbs up. Thank you, Brianna. Thank you, Gianna W. We've got two Giannas here this morning. As always, it's G squared morning. Sorry about that. All right, I'll give you another 25 seconds. Go, go. All right, my turn. All right, the first thing you should do is determine which molecules are conjugates on the right and left. And the conjugates differ by only a hydrogen. Well, they both have nitrogen, but notice this has hydrogens, this has hydrogens, Z has none. So this is the conjugate, and they differ by just a proton, H plus. Now, if we look at X, it has oxygens, so does Z, and that differs by H plus. So now we can go ahead and remember that on the right side, sorry about that H being all the way out in left field. Let's bring it closer to the G. Those are always the conjugates. So immediately I can write Y is a conjugate and Z is a conjugate. And you can abbreviate on test. Now, when I go from W to its conjugate Y, does it gain a proton or lose a proton? Count hydrogens. Goes from 3 to 4. That means it's gained or accepted a proton. What is a proton acceptor? A base. Now, if I look at X, when it goes from X to its conjugate Z, we're looking at it going this way. What is X? Does it gain or donate, lose a proton? Goes from 1 hydrogen to 0. I like that, 0. And that means it lost or donated a proton. What is a proton donor? An acid. Now, let's look at the reverse reaction. When Y goes to its conjugate W, it has 4 hydrogens and a plus charge, goes to 3 hydrogens, no plus charge. So did it gain a proton? Just count hydrogens. Shh, don't tell anybody I'm giving away that secret. discount hydrogen. Shh. But here we have 4, here we have 3. It has lost or donated a proton. What's a proton donor? An acid. And because it's on the right side, Y is a conjugate acid. Next, let's look at Z, the nitrate ion, and anion actually, and it has 0 hydrogens. When it goes to its conjugate X, it now has gained a proton. Discount hydrogen 0 to 1, that's gaining. What's something that gains or accepts a proton? I like that special effects. Accept the proton, it's a base. And that's how you do it. Now, one common mistake, and partly I'm guilty of it, I tried to show it's not true here. There's no rule which has to be first, which has to be second. You notice in the first example, I have the acid first. In the second example, I have the base. It doesn't matter the order. You have to look at the conjugates and does it lose or gain a proton? And you should know how to do this. Hint, hold on. Don't you like it when I'm subtle? So you should know this, which is why I went over this. Any questions on this before I move on?
Can we do maybe like 2 more?
All right, let's do one more. Oops, wrong color. And here's your one more. It's Special Request Tuesday. By the way, I take special requests every day of the week. So the question is, for the following equilibrium reaction, label W, X, Y, and Z, acid, base, conjugate acid, conjugate base. And I'm not saying that's the right order, but one of these is an acid, one of those is a base, one of those is a conjugate acid, one of them is a conjugate base. Your turn. Thank you, Brianna. Thank you, Gianna W. Remember, tonight I have my office hour from 6 to 7:15. Thank you, Anna. If you have trouble doing anything, you have any questions, always feel free to come to my office hour. I'll also have another one Wednesday night, tomorrow. Thank you, John J. I'm ready to go because your guys I've done it. All right, let's look at the conjugates. Conjugates differ by only one proton. So notice W has a chlorine, Y has a chlorine, Z doesn't. So these are conjugates. Now X has a nitrogen and so does Z. And if you count them, they only differ by one hydrogen, actually H plus. So X and Z are the conjugates. Now, by definition, the right side are always the conjugates. So I'll write that in. Now, if we look from W to Y, does it gain a proton or lose a proton? Discount hydrogens goes from 1 to 0. It donated or lost a proton. So what do we call a proton donor? An acid. And we're looking at the reaction going this way. Now, if we look at X, when it goes to its conjugate Z, does it accept a proton or donate? Count hydrogens goes from 3 to 4. And that means it accepted a proton. What is a proton acceptor? A base. And now we look at the other direction, going this way. And if we look at Y going to W, does it gain a proton, hydrogen, or donate it? Well, it goes from 0 to 1, so it's accepted or gained a proton. What's a proton acceptor? A base. And because it's on the right side, it's a conjugate base. And all we have left to do is Z. And here it is. Let's do it. Now, Z, when we're going in this direction, goes to X. Has it donated a proton or accepted it? Did it say, here, take my proton, or did it say, give it to me? Goes from 4 to 3, count the hydrogens. It's lost or donated a proton. And what's a proton donor? An acid. And because it's on the right side, it's the conjugate acid. And that's how you do it. And what I'd highly recommend you do, because sometime later today, I'll have our Zoom meeting today video posted in my YouTube channel. And by the way, everybody, thank you for making me a YouTube star. Not really, but thank you. And you'll be able to go back and do this and watch this. What I'd recommend you do is, once I put this up without the answers, you try it and then play the rest of the video for that question and do it for each of these. All right, let's move on. Now that you know about acids and bases and pH, something I should discuss All right, many years ago, I guess it was before all of you were born, but I'd already gotten my PhD in the late 70s, or even in the earlier 70s, but it got really bad in the late 1970s, was a problem in the United States and other parts of the world too. But since I lived in the United States, I'm familiar with that. By the way, most of my life I've spent in the Chicagoland area, except the 5 years I went to the grad school at Michigan State in East Lansing, Michigan. Even though I have spent that time, weeks at a time in Europe, in the Netherlands, Germany, and England, but most of the time, Chicagoland. All right, now, the problem was, mainly it was on the East Coast, I guess it's that way behind me. That way is east in my house. They had serious problems. Problems were plants and forests and farmers' fields, the crops or the trees were dying. In rivers and streams, the fish were dying, and it was a bad situation. And what they found was it was due to what's called acid rain. Now, what do I mean by acid rain? Well, let's look at something you've learned. And here we have the pH scale, which you should know. Hint, big hint, you should know. And it goes from 0 to 14. And halfway in between, 7 is called neutral. Below 7 is acidic. Above 7 is basic. And acid rain had a very low pH. And usually rain or drinking water, here they have between 6.5 and 8.5, but acid rain had a pH about 4 or 5, and it killed fish, aquatic life, and had a very bad situation in our forests, the soil, insects even. Well, what happened? Well, it turned out that the coal burning, and they show it over here, power plants were giving off sulfur dioxide as waste into the air from the smokestacks, and also nitrogen dioxide and nitrogen trioxide. And in the atmosphere, and I'll give you, and this will not be on the test, click, switches off, or on a quiz or anything else, but I think it's important. And I'm not going to balance this, but it's mainly this direction, will give you sulfuric acid. And also this sulfur dioxide mainly. And these react with the water in the air, in the clouds. And when it interacts with the water, it forms sulfuric acid. And when it rains, the water contains sulfuric acid, which makes it acidic and causes serious problems. I mean, it was serious. And finally, the government stepped in and enacted laws regulating the amount of different pollutants power stations and other industries could put up into the air. And it's an easy way to, I don't know, easy, but it's doable to, it's called scrubbing the gas waste before it is opened and let out into the air. Usually scrub it through water and other things. But anyways, because of that, within a couple of years, it had been reduced and almost eliminated. So what I wanted you to know about is pollutants, certain ones can get into the clouds. I like those special effects, but seriously can get into the clouds and react with the moisture in the air to form acid. And when it rains, the acid is in that water and can destroy things. I think in Europe, a lot of the old churches and things like that, and I think it was heavy in the Eastern European area, like Poland, when it was under communist country, and Hungary and those, the acid rain would eat away at the churches on the outside. I don't know what the material, the stone was, but it would destroy it. So I don't know how, I assume they've conquered it in Europe, but I'm not sure. So I wanted to talk about that. And I did. Now, let's do a new chapter. This new chapter will not be on quiz number 6, but a few points will be on test number 2 coming up in about a week or so. So let's get into that. And this is chapter 17. And this deals with nuclear radiation. Now, for the most of this, click, the switch will this be on a test or a final? Off. But I'd still like to go through this because you should know about this. Now, when we talk about nuclear radiation, there's something called a radioactive element. That's an unstable isotope of an element that will emit energy spontaneously to form a more stable isotope. Remember, isotopes of elements have, if you have the element in different isotopes, they have the same number of protons, same number of electrons, but different number of neutrons. Now, the energy they emit is called radiation. Now, there are different types of radiation, and click, the switch is still off. One is called an alpha particle, and this comes from a radioactive isotope, and it contains 2 protons and 2 neutrons. And obviously, because protons have a positive charge and neutrons have no charge, it has a positive charge. Next one is called a beta particle. Again, click, switches in the off position. A beta particle is a particle whose charge and mass are identical to electrons. Now, Dr. White has never worked in radioactive chemistry, or nuclear chemistry is the right name for it. In fact, sad story, years ago I was at a party where a lot of the chemists there, yes, chemists do party, we party hard sometimes, but anyways, were a number of them from the Fermi lab, and the other one, I can't think of the name now. And someone pointed out to me, this one woman, and said she just lost her husband. He died from a very rare lung cancer. And I said, did he work at Fermi lab with heavy radiation? My friend who knew them said yes. And so it's very dangerous, and I stayed away from that totally. I wanted to be an organic chemist anyways, but it can be dangerous. Now, I'm not a nuclear chemist, but why don't they just call this an electron? But they call it a beta particle. All right, next, a positron is a particle produced by unstable nucleus, which they all are. It has a positive charge. And finally, something called gamma rays. And gamma rays are very high energy radiation without mass or charge. That's just like light doesn't have mass or charge, and that's a form of energy. But gamma rays, by the way, in our universe, gamma rays will not turn you into the Hulk, Bruce Banner, but if you know that comic book character, but it's quite high energy. Now, when you have an isotope, you have what's known as radioactive decay. Switch is still off. And this is a process which a radioactive nuclide, which I guess is what they call the element, is transformed into a nuclide of another element as a result of emission of radiation. In other words, the isotope gives off energy to make something new, and when it does that, we call that radioactive decay. And the energy can be alpha, beta, or gamma rays. All right, switch is on. This is something you should know about. And that's the half-life of a radioisotope. The rate of decay, that's called the half-life. The half-life, abbreviated by T1/2, is the amount of time required for 1/2 of any given quantity of the radioactive substance to undergo decay to non-radioactive substance. So the half-life is, if you have 100 grams of compound X and it has a half-life of 1 day, after 1 day, you'll have 50 grams. So let's take a look at this. Hold on, I've got to correct this. I'll be done someday this week. All right, everybody see what I just wrote on the board, on the whiteboard? Let me read it. 3 points. If compound Z has a half-life of 2 days, then if you have 400 grams of compound Z, how many grams of compound Z will you have after 4 days? So what are we trying to find? Grams of Z after 4 days. And it has a half-life, T1/2, of 2 days. So how do you do this? Well, there's a formula you can use, but for my type of problems, here's the easier one. You have 400 grams. The half-life, after each half-life, you'll have half. So after 2 days, you'll have half of that, 200 grams. But you need 4 days, so another 2 days, you'll have half of this, which is 100 grams. And that's the answer. And that's how you do it. Now, if I look at the time, we're a minute into our break. Let's take a break now. Come back at about 9:57, and we'll continue on. And we'll also do our lab. I'll see you in 5. let's get going. Let's get comfortable too. All right. Now, the reason you should know how to do half-life, it's real simple. How many units of the half-life? You just divide things by half. Now, why is that important consideration? Why do I want to talk about it? Well, let's look at uranium half-life. Now, if you have uranium, everybody see the uranium half-life of uranium isotope U-238 on your screen? If you have 100 tons of that uranium isotope waste, after 4.5 billion years, you'll still have half of that that's radioactive. And that's, in my personal opinion, the problem with nuclear energy. They don't tell you what do they do with all that nuclear waste, because it's going to be around for eons. And let's look at now, I don't know where they use plutonium. It's got a half-life pretty short, 24,000 years. If you have 100 tons of plutonium, you've got to wait 24,000 years for it to be half of that. And that's the problem with nuclear energy. And so what can you do with that? Now, back in the late 80s, the US government had an idea. Let's find somewhere in the middle of nowhere, dig a very safe area, and then put all the waste of the United States in there. And they found near Nevada, Las Vegas, of all places, a mountain called Yucca Mountain, and that was called the Yucca Mountain nuclear waste. And they built here's the proposed design, where this was all underground construction in an area where there's no flooding and things like that. It's a desert. But here's the problem. Let's see if they have a picture of it. Let's go back to here. They came up with this idea how to make these waste containers, which I can't find a picture of. And they did a test. And the test was in the Yucca Flats, they filled these containers with nuclear waste. After about 5 years, 4 or 5 years, they were leaking. They weren't going to last 24,000 years. They weren't going to last a couple million years. And also, the people in Nevada said, we don't want this in our backyard. And so it was canceled, wasted a lot of money. And we still have the problem, how do we deal with nuclear waste? Which is why I personally don't think, and thank God we're doing wind and other things, is the way to go for low pollution energy. All right, let's move on. And notice for the half-life, I should have said, no, know this. All right, switch is still on. When we talk about nuclear energy, there's two main types of nuclear reactions I would like you to know. The first one is nuclear fission. Fission is the process where you take a large nucleus, a large element, and split it by energy into two smaller ones. And when you have that split, it gives off a lot of energy. This is called nuclear fission. And you should know this. Hold on. It's Subtle Tuesday. And again, this is not for quiz 6, but test 2, you should know some of this. All right, so nuclear fission, big nucleus split into smaller ones, and you get a lot of energy. And where does that use in nuclear reactors? That energy, when the split happens, is in the form of heat. Heat is used to change water from a liquid to a gas steam that drives turbines that makes electricity. So nuclear fission, large split into small. You should know, example, nuclear reactor. Now the other type is called nuclear fusion. And nuclear fusion is a process where you take a small nuclei, two of them, slam them together to make a larger one. I don't know if you just slam them, but they collide together with immense energy is given off when that happens. And where's that happening? The sun. You take hydrogen, two of them together, and you make helium. So next time you see the sun, you really shouldn't look at it without proper protection for your eyes, or you see sunlight on the ground, the reaction that's making that is nuclear fusion. Two small atoms or elements coming together to make a larger one, and it gives off a lot of energy. Just look at some of the videos of the surface of the sun. That's a lot of energy. Now, how do you remember the different and the examples? Well, the way I did is fusion, U is like the sun. Think of fusion, sun, fission, the other one, which is nuclear reactors. And you should know this, both of these.
Do we need to know the definitions or
Yes, both.
for the test too, right? For next week.
For the test, not the quiz. And you should also know, if I ask, give an example of nuclear fusion, you would put down the sun. If I were to ask, give an example of nuclear fission, you could put down a nuclear reactor. Does that help? I think it was Anna. Did you ask that?
Yes.
Well, does that help you?
Yes.
Thank you. And as always, all questions are good questions. Thank you for your question. I'm sure you helped out the other students. I don't know if I said this, but two things. I only bet when I know I win. That's just my personality. Even though when I've been at the crap tables in Nevada, where I would go there in the past, where I had to speak at a large conference, and it was at like one of the casino hotels, I'd go to the crap tables and I do well. I could walk away with about 5,000 a night. Don't ask me how, but I'm not a gambler. I've never been to any of the casinos in Chicagoland. But anyways, what was I going to say? I was looking at this. You should know this. What's a nuclear reactor? That's a fission. And you should know fusion is the sun. That's the chemical nuclear reaction that goes on there. And I lost my train of thought when I was thinking about times I was at the tables in Reno. That's where we used to have conferences. Fun time. Chemists know how to party hard. All right. Any questions about this? We've ended that chapter. So now it's Boy, I haven't used this in a while. Ooh, red on red. It's lab time. Now, if you notice, we've done all the labs in the Carolina kit. And I said, no, I wanted to add one more lab. And I teach, as you know, both at College of DuPage and are also Elgin Community College. In the past, I've taught this semester, I'm teaching organic chemistry there, but their equivalent to Chem 1211 is called Chem 112. And at that school, I'm able to write some of my own labs, and I did. So one of the fun labs I wrote, and students like this, but since you don't have all the chemicals, I will just give you the data, but you got to use the thought process, I like my special effects, to figure out what's going on with that data. What's this lab? Well, let's take a look at it. It's called Doing Chemistry with Food. Ooh, that sounds exciting. Everybody see that on your screen now? Thank you. And this you can download from Blackboard. Now, I should warn you, this lab uses some very, very dangerous chemicals. Real dangerous. Kidding. But anyways, all the items that you find in your kitchen or supermarket are made up of chemicals. And yes, chemicals. And the food you eat and the ingredients that you use to make various food dishes are composed of atoms and molecules, which is why whenever I hear someone say, I hate chemistry, I laugh because everything around you is chemistry. But what they really mean is I hate whoever taught chemistry to me. My sister was in that boat. She hates chemistry to this day because she had a bad teacher. When she took chemistry, she's 7 years older than I am, and I didn't know chemistry that well. My father did and helped her through high school chemistry, or she would never have passed. But anyways, don't tell her I said that. But the chemistry that you learned in this class can be applied to the food items in your kitchen. In this lab, you will be investigating the acidity or basicity of various foods and cooking ingredients. Remember, an acid is a proton donor, a base is a proton acceptor, and we can measure the basicity or acidity of solutions by measuring the pH. If the hydronium ion concentration is greater than hydroxide, it's acidic. If the opposite is true, it's basic. Now, instead of just measuring those concentrations, we use pH. And here's the formula. Remember, pH less than 7, acidic, pH greater than 7, basic. And the pH of the solution can be measured by pH paper. Everybody see on the screen the hydron, I don't know how to pronounce that. I always call hydronon ion pH paper. And that's the most common brand. And if you notice here, you see how you have a strip of paper coming out of the roll. And on the side, you have a color code. 0 is red, 13 is almost blue, 7 is a light green, 10 is a very, very dark green, almost blue. What you do is you take that strip of paper, and looks like this, we have like this paper right here, except it's on a roll, and whatever you want to test, you put a drop on there and look at the color and match it to the scale on there, and that will tell you the pH. Now, it only goes from 0 to 13. If it's real dark blue, you could also call it 14. But for this lab and everything we do in the lab, this is very handy. There are other ways of measuring pH, but this is the quickest and actually the cheapest. Not that the rolls are that cheap, but compared to other equipment, it is. Now, what are you going to be doing in this lab? Well, let's find out. Now, you can look at this video to see how to use pH paper. I'll let you do that on your own. Now, in this lab, you'll be reacting acidic foods with basic foods in the following reaction and determining the pH of the food after they're being reacted. This is called the neutralization reaction. You have acidic food, HA, and a basic food, you have proton transfer to make a salt. And what this should do is change the pH. Now, the other thing, and I'll explain in a second, you'll be determining if a additive, something you're adding to the food, is it a strong, and you'll be doing base or a weak base. Now, one of the interesting things, both at COD and ECC, is we do not use what's called, I call it, because I worked in industry, city water. That's the water that comes out of your tap in your kitchen or your bathroom or your utility room that comes from the city. And in our case, Lake Michigan. That has a lot of ions in there that can affect many things. So what we do in a chemical lab is pass it through a special series of filters that takes out those ions, and that's called deionized water. Now, water should have a pH of about 7. Should. It doesn't mean it has. In fact, one problem I was called in to solve at one of the companies I worked at, and they had been working on it for months, and it was costing the company hundreds of thousands of dollars for months. They've wasted over $1 million. I went to the plant in, where was it? No, Cleveland, I think it was, outside of, no, it was outside of Toledo, or in Toledo itself. And one of the problems was the pH of the final product, and it used water. So I asked the question, what's the pH of our water here in Toledo? They didn't know. After I got sort of upset with them politely, but let them know I wasn't happy, I said, give me some, let's take some water, stick in pH paper, look at it, and it was amazing. The pH was at 8.5. It should have been 7. Well, it wasn't, and that was part of their problem. Problem solving, never assume, which is what they did. And luckily, I had a mentor that taught me that was one of the first rules: never assume something. And 2, common sense is not common. The most obvious, straightforward answer is the one most people ignore. And that's true too. Common sense is not common. Anyways, the first thing I have students do is measure the pH of the deionized water. And I'll tell you this, deionization affects the water by taking out the ions. And if you were to measure the pH of DI water, that's short for deionized water. And for this lab, I'm giving you all the data. Thank you, Dr. White. You're welcome. It's 6.7. Now, let's look at the lab. In this lab, you'll be reacting different food items. They're really condiments that you can put on a hot dog or some of them, or a hamburger, with first sodium bicarbonate and then with sodium hydroxide. Both are bases. And for all these, the procedure is the same. You'll take about 10 milliliters of DI water, about a gram of the food, put it in a beaker, mix it up, then measure the pH. Then you'll add some baking powder, stir it, measure the pH, add some more, and then add a lot more. And then put it in the waste beaker, or for really, we dump it down the sink. It's not hazardous. Now, the hazardous chemicals you'll be testing are, this got out of range, are, no, it's okay, vinegar, orange juice, ketchup, dangerous one, tomato paste, lemon juice, mustard, and Coca-Cola. And here's the table. Here's the initial pH. Here's observation. Remember, sodium bicarbonate, you saw that with the airbag lab, gives off carbon dioxide, and that's why you see the bubbles. And notice after each one, there's a change in the pH from where you started. And this is based on data when I've seen students do the lab. Now, you'll do the same type of reaction with sodium hydroxide solution. And you'll put 10 milliliters of DI water and about a gram of the food in a beaker, mix it, measure the pH. We use about a 1/10 molar sodium hydroxide solution, add a couple of drops, mix it, add a couple of drops, and then add a lot more drops. And each time you'll measure the pH. And again, the same dangerous chemicals, vinegar, orange juice, ketchup, tomato paste, lemon juice, mustard, and Coca-Cola. It's fun to watch because tomato paste is not pleasant to work with if you don't know how to work with it. It's that thick stuff. It's hard to get off a spatula, but I teach students how to do that. And here again, here's the initial pH observation after the first addition of sodium hydroxide, second and third. And here are the questions you have to answer. And for the lab, all you have to do, you don't have to do anything with your kit, is download this. And by the way, I have here for the sodium bicarbonate, if you've never seen it, the two videos for baking powder and vinegar in what's called a rocket. Don't do that at home, it's dangerous, but it's fun to watch the videos. And you'll here answer these questions, and you'll hand in the questions next week. And don't forget to hand in the lab that's due today. With that, I'll say I'm done. Don't forget, tomorrow after class, I'll be sending out the password for quiz 6, 1, 2, 3, 4, 5, 6. And you'll be doing that. You'll have till Thursday, 11 a.m. I remember I made a mistake in the email I sent out yesterday with the calculations for the titration lab, that I said the extra credit project is due tomorrow. It's due a week from tomorrow on the 7th of December. And if you have any questions, come to my office hours. And with that, I'm going to say I'm done. Gang gesund. Goodbye now. Remember, gang gesund, go in hell. Bye now.